Bingham plastic, it could be used, if necessary, for some real oil-based mud systems. And sometimes some drilling engineer will say, oh, I want you to use Bingham plastic. Now, I would use it, but I would still argue the case for Herschel-Bulkley, and I would use what I've just talked about to argue that case. And Power Law may also be used for some water-based mud systems. Basically, these two statements come from the old oil field. Basically, that's what's always been done, so that's what people still do. Baroid have been using Herschel-Bulkley for the last 12 years. This is 2006. They've been using it for the last 12 years. And they don't use Bingham, they don't use Power Law. We still have Bingham and Power Law in our software, but it's not recommended to use them. You should use Herschel-Bulkley. They're there because drilling engineers might ask you to use them, not because they are accurate. Now basically only 0.5%, 0.5% of all fluids used in the oil field can be described by Bingham plastic or Power Law. The Herschel-Bulkley yield Power Law can describe these fluids. It can describe that 0.5%, but more importantly, it can also describe the 99.5% of all other fluids which actually lie between the Bingham plastic and the Power Law. So that's why you should use this and not use these. So just in summary then, as can be seen, like basically the three models attempt to show the relationship between shear stress and shear rate in slightly different manners. I'll just summarize what they do. Bingham gives you tau equals yp plus pv times gamma. Power Law, tau equals k times gamma to the power of n. Because it's to the power of n, that's why it's called the Power Law. The yield Power Law, or the Herschel-Bulkley model, is tau equals tau 0, which is the same as yp, plus k, which is similar to pv or k in Power Law, times gamma to the power of n. So you've got the Power Law part and the overall things similar to Bingham. It's got the advantages of both of these models. But as I said, it will describe 100% of the fluids in the oil field, pretty much. Whereas both of these combined only describe 0.5% of all the fluids you might come across in the oil field. So using them is a bit daft, really. So you can now describe the differences between these models, and therefore you can actually describe some of the limitations of the models as well. One thing I want to draw your attention to before you wander off thinking Herschel-Bulkley is the best thing ever, some of the assumptions which all of these models make. The drill string is the first one is something which is not true in any borehole I've ever seen, and that is that the drill string is placed concentrically in the hole. Now, as you know, eccentricity changes the pressure, changes the velocity profile in the annulus, and it also therefore changes the pressure, changes the flow behavior in that annulus. So it's making an assumption that you've got concentric pipe placement in the borehole. Therefore, all the models should really be overestimating the pressures when you use them to calculate pressure, regardless of which model it is that you're using. However, the drill string is not being rotated. That's the second assumption. It's not taking into any account the rotational speed of the drill string. Now, there's a fair bit of work going on in Baroid at the moment, looking at the rotational speed of the drill string and the effect on the flow behavior in the annulus, and also the effect on pressure, the effect on the annular pressure drop due to rotation of the string. And we know that as you rotate, pretty much if you look at PWD data, if you rotate the string, the pressure rises. So assuming that the string is not being rotated is basically underestimating the pressure slightly. So perhaps these first two assumptions actually cancel each other out to a certain extent. Not completely, but they do. You'll still be overestimating the pressure, I would think, a little bit. But the third assumption is that the sections of open hole are circular and of known diameter. Now, we all know that when you do a caliper, they're very rarely completely circular, they're more elliptical, and also they're very rarely all one diameter. You've quite often got washed out areas and ledges and so on. So the models are all assuming a perfect cylinder in your open hole. That's another big assumption to make. They're assuming that the drilling fluid is incompressible. Water is relatively incompressible, but an oil-based fluid is pretty compressible. And we know that the changes in density and viscosity can occur at pressure down the hole, at depth, under a great deal of pressure. you've got a compressibility factor. And that depends totally on the base fluid. These models by themselves do not take into account the compressibility of a fluid. And they also don't take into account temperature effects. Basically, they're assuming the flow is isothermal, as in there is nothing in those models that allows you to adjust the rheological properties of the fluid due to temperature. So most of the software that we use does not address these assumptions. So most of the software like Insight, WellPlan, Planet does not have any, does not allow you to adjust the temperature and pressure, eccentricity and so on. Well, WellPlan actually does allow you to put in some factors, but as I'll explain some of the limitations in WellPlan when I'm going through the WellPlan software itself. Insight and Planet do not allow you to take into account pressure and temperature effects or eccentricity or rotation. So be aware of that. Now DFG Plus, the DFG, the software that Baroid sometimes allow us to use, and we will use it occasionally on some hole cleaning jobs, it does take into account the thermal effects, the pressure effect, compressibility of the base fluids, and it takes into account eccentricity to a certain extent, and soon it will be also taking into account rotational speed of the drill pipe as well. At the moment it doesn't take into account the rotational speed. But be very aware that these are limitations. So as soon as you start rotating the pipe, or as soon as you start drilling an angled hole, the pipe's eccentric on one side of the hole, it's being rotated, pressure should be increased due to rotation. If you know that the borehole is out of gauge, you know that that's something else that can affect your results, and also the temperature and pressure effects. Make sure you understand that. So now you're actually able to describe the three main models that our software can be used for. We can describe the sources of inaccuracy within those models, and we can work out which model is best for hydraulics analysis, as in Herschel-Bulkley. I hope you've all agreed on that after this. And we're also able to list the limitations in our software and therefore understand where sources of divergence from reality may actually occur.